Yeah, there we go. Okay, so this talk is about Speculaas, and I guess you all know what Speculaas is. It's a bit like this, and for our Belgium guests, I think it's called Speculaas in Belgium, so whenever I go to give this talk in Belgium, I will rename this application. It's about specification-based testing and development. And here's a nice description. Specification-based testing is a standard, expressive, powerful, integrated system for specification and testing. So Speculaas is all of this. And I didn't think of this myself, of course. I took this from a clojure.spec, all this, well, this description, also the actual idea of writing Speculaas. Also, initially it was called spec.js, but that name was already taken, so that's why I came up with Speculaas, because it has a name, the word spec in it. So why did I develop something like this, or why did I steal this idea? I love JavaScript a lot, especially since I'm recently doing a lot of Java again, so that makes me appreciate the dynamic language that JavaScript is. But it also has a downside, because if it's dynamically typed, you will have to write more tests or debug a bit more or make sure that your program is going to run. And writing tests is not that much fun, in my opinion. It takes lots of time, and yeah, it's repetitive work and it's a bit boring. And also, even if you write wonderful tests, you will still have the situation that you will get some runtime errors, because you will always forget some edge cases. So what I did is I created Speculaas, and Speculaas is based around the idea of predicates and specifications. And this is a bit of boring, well, hopefully not too boring theory, but predicates are just statements about a variable, about a function, about a data structure, etc., etc. And predicates can be one of those in Speculaas and in clojure.spec. Notice that I used the word closure again. So a predicate can be a very simple Boolean operator or Boolean function. It can also be a more complicated predicate expression. It can be a combined expression, so you can combine different expressions, predicates, using AND or, so you can compose a whole hierarchy of specifications. I use the word predicate and specification a bit loosely coupled. Predicates is basically the overall arching principle, and specifications are the actual specifications that can have a name in Speculaas. Arrays, maps, and sets, even though these are data structures, can also be used as predicates. And I will give some examples of that next. This is the first example. The actual predicate is integer here. As you can guess, it will see if the parameter is an integer. And the s dot is valid. The s is the namespace of Speculaas. Is valid is just a function that checks if this predicate is valid. And if you say is valid integer 3, it will probably say yes, that is true. You can also use an anonymous function for this. In this case, we use a function that sees if the variable is odd or even. In this case, odd. So if is valid anonymous function .to, it will apply your parameter to this function. The third example is something like an array. So I use an array as a predicate, and in this case it will check if the actual value is within this array. And it will return true in this case, because 2 is part of this array 1, 2, 3. Well, this is pretty trivial. It becomes a bit more interesting if you combine predicates. And for example, s.tuple creates a predicate which consists of 3 integers. So it creates a data point in this case. That's why I defined this as a point, which should consist of 3 integers. So whenever I try to put 2 integers in it, or an integer and any other data type, it will complain about this. So in this case, s is valid point 1, 2, 3, 4, 1, 2, 3 is a valid data point. So it will return true. More examples. Bear with me, there will be some code later, and I will give some demo, but this is just a bit of an introduction. You can compose predicates. In this case, I use the OR operator, so the spec.or operator. And basically it says here a name or an ID, that's the name I give to this specification, should be either a string or an integer. And in this case, if I say is valid name or ID 1, it will actually say yes, that's valid because this is an integer. And even the word 1, the string 1, is also valid because in this case it's a string. If I would try to put in a floating point number in here, it would complain and say, well, sorry, this is not a valid predicate. Finally, another combination. You can see here that I can define a predicate which is called, or specification which is called odd, so it determines if a variable is odd, and it is odd if it is an integer and it is odd. It's a bit of a weird combination in this case, but it serves to show how the AND operator can be composed with two different predicates, so I can build larger structures. And the next step it says, well, I have a collection of odd numbers. It should have at least one number, so that's the plus operator. This is your standard regular expression operator, so plus means one or more. And it should have one or more odd numbers. So here I reuse the odd specification that I defined previously. In this case, I can say, well, is this valid? I have a list with two numbers, 1 and 3. Now, in this case, it's valid because both of these numbers are odd, and it has at least one element. And in the last case, 1, 3, 6, it would say, well, sorry, this is not odd because it is not a collection of odd numbers because it has 6 in it. So, a couple of examples of specifications. Now, how can you use these specifications? There are a large number of operators, but I show the first 3 ones here. The is valid we have already seen. What it does is it checks your specification against input. So if 3 is an integer in this case, that's a valid specification and says true. If you want to have some more information, just true and false is not that much information. You can say, well, does this conform the value 3 or the string 3? Does this conform to the specification is integer? And in this case, it will say, no, sorry, it doesn't, and it will dump a string or return a string which has Node.js invalid. Even that is quite limited. The third variant is easier to use or gives more information because you can say, okay, I've seen that this specification is not correct or that this input is not correct. So I use the explain function. And when I use explain, it will nicely show what part of the specification or what part of my input didn't fulfill my specification. And in this case, it says, well, the value 3 fails the predicate is int. Now, this is pretty straightforward, but you could combine a whole data structure and it would nicely pinpoint what part of your data structure doesn't fulfill your specification in this case. So this works completely recursive. You can build it up. Well, this is a little bit of theory, so you have some background on what you will see next in the demo. It's kind of a live demo, which means I will do some coding. Most of that is prepared, so it should work in theory, but I will also change some code, and in general that will fail most of the time. So what you see here on the top is a bit of code. It's just the standard Node.js code or JavaScript code. Initially, I will set it here. Before the previous talk by Rebecca, I didn't know that console.log could do a bit more than just dump 1 or 2 levels. It's nice to see that there's more possible, but in this case, I just defined a function inspect that nicely formats my variables, and I will execute it here. Now, I defined the function inspect. These are just a couple of helper functions. This part is int, is string. Those are the first predicates I'm going to use, and they are important from utils library, so even that is not that exciting. But now I defined 2 predicates, and now I can start to use them. So in this case, let's see if 2 is a valid integer. And as you can see, yes, it's a valid integer. Well, that's not too remarkable, I guess. And when I try to see if the number 2 or the string 2 is also a valid integer, it says, no, sorry, it's not a valid integer. When I would like to see why, I can do the explain function. In this case, it says, well, value 2 fails the predicate is int. This is just one single level of specification and validation. Now, this is just it was just a very short introduction. Next, we are going to build up a complete data structure, a way more complex data structure, which contains a game of cards. And the game of cards has several things. Of course, it has cards, it has players, it has a deck, etc., etc. So in this demo, I will show you how I build up this data structure. And the first thing I do is I create a suit of cards. So that should be clubs, diamonds, hearts, and spades. Well, that makes sense, I guess. I also define a rank. A rank should be anything, should be everything from 1 to 11, and jack, queen, king, and ace. And I also need a deck of cards, and a deck of cards are all the possible combinations with suits and ranks. And again, I'm going to use the word clojure, because the original clojure way is code's way more compact in this case, but this is the Node.js equivalent, and it also, of course, works. I could do now inspect deck. And this is okay. This is the first time I type some code and it immediately fails. Yeah. So it generates a deck of cards. Again, this is still some initial definitions. The next part is where I define an actual card, and a card contains is a tuple of a rank and a suit. So this is a definition of one playing card. I defined it right now, and I can also define a hand of cards. And as you can see, a hand of cards says is star card, so it's 0 or more cards. So you can have an empty hand with no cards in this case. And now let's show something that you can actually do with these definitions, with these specifications. Since I have a specification of a card, I can say, let's generate a couple of those cards. 12 in this case. So this is a first example of how you can generate data that can later be used in your actual testing, for example. So now we have defined a couple of cards. But we are going to continue building up this whole game of cards. So the next step is we create a player. Let's see what that is. So now we have a player. A player has a name, of course. It will have a score. And a player consists of a name, a score, and a hand. So there's a hand of cards. So we are continuing building this data structure. Okay. And one more step, players. We have more than one player, of course, in a card game. It can be even 0 players, then it's not a very interesting game, but players is a collection of player. So again, we build upon current data structure. We build a deck. And finally, we build a game. And what you can see here is a game consists of both players and a deck. So I have fully specified what a game should look like, how the player should look, how a deck should look, etc., etc. Now this is a specification, and we can start seeing if this is a valid specification, or if the data is valid. So let's define Kenny. Kenny is a player. I don't know much about playing card games, but I think Kenny Roche is probably famous. But let's see, we define a Kenny which has a score of 100.3, and that is invalid because we specified that the score should be an integer. So let's see if this works. Well, you see, Kenny is not a valid player, probably because of its score. And we can explain why this is not the valid input. And again, you will say predicate fails spec. I didn't use this nice console dump with different levels, so you still see this object. But you can see the player fails the predicate is int. So we can fix that again. We make this a nice integer. We evaluate it again, and hopefully now Kenny is a valid player. And indeed, now it says true. And if I do an explain now, there's not much to explain because he's valid and it says success. So that's about it. Okay. Now we have a complete game, which you can also validate. So I defined the game, and it consists of a deck. It consists of a player, and this player is holding in his hands 2 bananas. And again, it should say, well, sorry, but this is not valid. I hope. Yeah, like you can see here, it says false because he's holding bananas, and bananas is not valid in playing cards, obviously. Okay, now that we have defined all the data structures, we can start generating players and start generating games. Let's first try this with the specification of a player, and based on that generate one single player. And you can see generator creates a player with an empty name, a 0 score, and a handful of cards. Now, the reason that this name is empty and the score is 0 is that the test generator, the properties generator, initially always starts with a empty string and with a 0 score. So this is a nice test input because you can see if it's allowed to have players with no name, for example. So this is a very nice test case. And because we also already defined the game, which is a deck of cards and a collection of players, we can also generate a complete game instead of just a player. I assigned this to a variable game, and if I inspect this, well, this is not a very, well, it is a game. This initial game has 0 players, it's an empty array, and it is a deck of cards, so there are some cards laying on the table, 3 cards, and but it is a valid game, because you can have games without players, obviously. I can try to generate a game again, and hopefully this time it's a bit more interesting. Yeah, well, this is a more complete game. This game has a couple of players. They are all, well, they don't have a name, anonymous players, but could be kind of poker, so you try to be anonymous, I guess. And it has a, well, all these players are holding cards, Queen of Diamonds, 8 of Hearts, 5 of Clubs. We have 5 players, and we have an empty deck, so there are no cards on the table left. So this again is test input that can be used for any test. Right now this generates just one game, but I can easily as well generate hundreds or thousands or millions of games, because I can, yeah, you can generate as much data as you want. So this is about generating inputs. How am I doing on time, by the way? Because running out, okay. Well, that's a good thing. Because that was the part of the demo. This is for generating test data, and that's quite a nice thing, because then you can write your unit test and generate your unit test, and that saves a lot of time. However, most of the time, still some problems will escape. And for that you can also specify functions, like it's done here. And what you can see, if I have a very trivial function, it's called ranged random, and it will generate random numbers between start and end. When I want to test this function, if it actually does what it's supposed to do, I can create a specification, and that's what is called fdef, function definition. And I say, okay, this function range random, what do I expect from this function? The first step is I specify the arguments. I shouldn't do this, I guess. I specify the arguments part, and in this case the arguments part, waving doesn't help, I guess, so I point to mouse. My arguments are a concatenation of start and end. So the start and end here should be both integers. So I specify here that this should be an int, and the end should also be an int. I also specify that my args I can use, the start should be less than the end. So that's the input I specify. The return value, well, I want to know that is an integer, because I expect a ranged random number, so it should be an integer. So that's part of the return spec. And I can also define a function, fn here, that states a predicate about my function. So it relates my return value to the input arguments. And what I say here is, well, my return value, or my return value should be a value that should be larger than the start, or larger equal than the start, and smaller than the end function. So this is a complete specification of the ranged start function. Now I can use this function either to test my implementation, if it's correct. So I can use it in a unit test, and I created something here. I shouldn't do this. But it says stest check range random. So it will check my function implementation against my specification, completely independent. Even more important, I can use this specification to also do runtime instrumentation. So if I have created the specification, I can say instrument this function, and on my running application, it will continuously check how my function is called. So even in a runtime environment, I can dump information and pinpoint exactly where something went wrong. So that's the second powerful part of the specification. Okay, now for references, last time I used the word clojure. If you really want to see the rationale behind it, why this is created, Rich Hickey, the inventor of Clojure, can explain this way better than I can. But he put a very nice rationale and overview on the clojure.spec homepage. And if you want to try it for JavaScript or Node.js, because it's Amsterdam.js by all means, then you can have a look at the website, Speculaas website, and you can download and hopefully use this implementation. And so you will never have to, sorry, backwards, you will never have to debug again, and you can just write specifications and be done. Okay, that's it.
Thank you, Maurits.